Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 1 on complete factoring. Alright, so we've been doing some factoring lately, right? And we've seen three different types of factoring. GCF, greatest common factor. The difference of perfect squares, where we use facts about conjugate pairs of binomials to factor. And where we factor trinomials, where the leading coefficient is 1. Today we're going to look at something called complete factoring. So let's get into it right away, but just with some normal numbers. All right, so complete factoring of whole numbers. This is something that you've done for a number of years. Now remember, factoring is the process of writing a number or an algebraic expression as an equivalent product. When we write the product such that no other part of it can be factored, then we have completely factored the number or the expression. Now, I always want to make sure that you understand what I'm talking about with numbers before we go on to the algebra. All right, so let's take a look at complete factoring of numbers. Exercise number 1. Consider the number 12. All right, considered. Letter A, factor the number by writing it as the product of two whole numbers. Now, there's lots of different ways that you can factor the number 12, or at least a few different ways that you can factor the number 12 as the product of two whole numbers. And I'd love to just say, hey, go ahead and do that, okay? But let's do it together so that we start with the same numbers. So we could say that 12 is equal to 2 times 6. And if I said to you factor the number 12 and you wrote down 2 times 6, I would give you a 100% because you had written 12 as an equivalent product. Now, letter B. Why doesn't this represent the number 12 factored completely? All right, well, I'd like you to think about that. Look at these two numbers and tell me why that's not factoring 12 completely. Well, 12 has not been factored completely because 6 can still be written as a product. Now you might say, well, so can 2, because 2 can be written as 1 times 2. But we're never going to break down a factorization as 1 times something else, okay? But we can break down 6. 6 can be factored more. So the answer to this question is because 6 can still be factored. 6 can still be factored. All right, so now letter C says factor 12 completely. Well, to do that, right, we can say 12 is equal to 2 times 6, and 6 is equal to 2 times 3. So now 12 is equal to 2 times 2 times 3, and this is factoring 12 completely. Now, before we move on to factoring 30 completely, you might say, well, what if you didn't start with 2 times 6? What if you started with, let's say, 4 times 3? That'd be fine, right? That would be factoring 12, okay? But now it's the 4 that isn't factored, right? So then we could say, well, 12 is equal to 2 times 2 times 3. And notice, we have exactly the same thing as we have here. It doesn't really matter the order in which you factor, right? Eventually, you just have to make sure that nothing else can be written any further as a product of whole numbers. Okay, that being said, letter D asks us to factor 30 completely. So this time, because there are multiple pathways to doing that, I'd like you to pause the video and factor 30 completely. All right, well, there's actually a lot of different ways to start. We could start with 30 equals 2 times 15, or 30 equals 3 times 10, or 30 equals 6 times 5. Lots of different ways to do it, but they'll all turn out to give you exactly the same complete factorization. For instance, if I said 30 equals 3 times 10, right, and then 10 is 2 times 5, right, then I would have 3 times 2 times 5. That would be factoring 30 completely. Or if I said 30 equals 2 times 15, I could then say 15 is 3 times 5, And I'd have 2 times 3 times 5. Now keep in mind, of course, that these two things are identical, right? Because multiplication can be written in any order you want it to. I could even do the 6 times 5, but it would give me the same thing, as I'm sure you're aware. All right, so now we want to move into the algebraic realm. All right, and we want to make sure that we think about it the same way. Complete factoring of polynomials. So far, we have factored polynomials using only one step or technique, right? We've either done a GCF, or a difference of perfect squares, or a trinomial factoring. Sometimes we will need to use multiple steps if we're completely factoring the polynomial, like we just did with those whole numbers, right? Maybe we have to factor once, then look at what we have and factor again. So let's take a look at exercise number 2. Consider the trinomial 4x squared plus 20x plus 24. Letter A, write this trinomial as an equivalent product of its greatest common factor and another trinomial. Okay, so this is something that we did a couple lessons ago, and basically I'm just asking you to factor out a GCF. So pause the video now and see if you can do that. All right, well, the GCF of this trinomial is the number 4, right? 4 goes into 4, it goes into 20, and it goes into 24, right? So I have a GCF of 4, and therefore I can say that this thing is equal to 4 times x squared plus 5x plus 6. Now, a couple lessons ago, when all we were doing was GCF factoring, we would have stopped at this point. But now let's take a look at letter B. Factor this additional trinomial to express the original in completely factored form. All right, so here's the point, right? We've now written this thing as 4 times x squared plus 5x plus 6. But this all by itself can be factored, right? So in our last lesson, we looked at how to factor trinomials, right? And we do that for, just ignore the 4 for a minute, right? We would be looking for two numbers that have a sum equal to 5 and a product equal to 6, right? Those two numbers are 2 and 3. So that whole thing factors into x plus 2 times x plus 3. But what we also can't forget is that 4. Right? It's not like we get to suddenly like drop that GCF. When we say that we're factoring it out, we're not like factoring it out and throwing it in the trash can. We're just writing it as 4 times x squared plus 5x plus 6. And then we're taking x squared plus 5x plus 6 and writing that as x plus 2 times x plus 3. And that is factoring completely. All right? So that's really what we're going to focus on for the rest of this lesson. Whenever we're asked to completely factor, and watch for that word, completely factor a polynomial, we should always look to see if there's a greatest common factor that exists that can be factored out to begin. Always, 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 always look for a GCF first if you see complete factoring, okay? So let's take a look at exercise number 3. Rewrite each of the following trinomials in completely factored form. All right, cool. So let's take a look at letter A. Here we have 5x squared plus 10x minus 40. Now if we look at the 5, the 10, and the 40, we see that that trinomial has a GCF of 5. So that's going to be my first thing. All right, before I do anything else, I'm going to first write this down as 5 times x squared plus 2x minus 8. All right, now, after I've factored out that 5, I now want to look inside of the parentheses as x squared plus 2x minus 8, and I want to go back to what I did in the last lesson. I want to think about two numbers that have a product of negative 8 and a sum of positive 2, okay? Those two numbers are x plus 2, well, those two numbers are positive 2 and negative 4, but that gives us 5 times x plus 2 times x minus 4. All right? Ooh, I just made a mistake, right? Maybe you can spot it, right? 2 times negative 4 certainly gives me negative 8. But 2 plus negative 4 would give me a negative 2, not a positive 2. In fact, correct factoring would be this. Now, by the way I spotted my mistake was when I was looking at these two binomials and thinking about what I would get if I multiplied them back out. I realized I wouldn't get a positive 2 there, I'd get a negative 2. And that made me say, whoops, I've made a mistake. Never forget to kind of take a look and think about what you have. Pause the video now and see if you can completely factor letter B, which is very, very similar to letter A. All right, in this case, we have 7, 21, and 70. The greatest common factor of those is the number 7. So what I'm going to do is I'm first going to factor that 7 out, leaving me with x squared plus 3x minus 10. All right, very similar to the last one, right? I'm thinking about two numbers whose product is negative 10, but whose sum is positive 3. Those will be positive 5 and negative 2. This time I'm pretty sure I have it right. And so that is the complete factorization of that trinomial. All right? Now let's take a look at two that are a little bit more confusing and really take a look at letter C. Let's take a look at it up close. I want to factor negative 3x cubed plus 21x squared minus 36. Now, all right. This is the first time I've seen this, where the leading coefficient is negative. Leading coefficient is negative, all right? Now, please note that for negative 3, positive 21, and negative 36, definitely 3 divides into all of them. But if the leading coefficient is negative, then you want your GCF to include that negative. In other words, I want my GCF to be negative 3, not positive 3. Now, let's take a look at that first step. This is a little bit tricky. So the first thing I want to do is factor that negative 3 out. All right. Oh, actually, not just negative 3, but negative 3x, because we have an x squared, and an x cubed. So we're going to factor a negative 3x out. Now, what do I have to multiply by negative 3x to get negative 3x cubed? Well, that would be x squared. Here it gets a little bit trickier. What do I have to multiply negative 3 by to get positive 21? That would be negative 7, and I have to have an x to get an x squared. And then what do I have to multiply negative 3 by to get negative 36? And that would be positive 12. All right. Now again, if you're not sure whether it's right or wrong, think about multiplying that negative 3x back through, right? Negative 3x times x squared would be negative 3x cubed. Negative 3x times negative 7x would be positive 21x squared, and negative 3x times positive 12 would be negative 36x. And now, just like before, I have to then go on and factor this, which means I'm looking for two numbers whose product is negative 12, or sorry, product is positive 12, and whose sum is negative 7. Because the product is positive and the sum is negative, the two numbers must both be negative. And in fact, they end up being x minus 3 and x minus 4. Negative 3x times x minus 3 times x minus 4. All right, what I'd like you to do is pause the video now and see if you can do letter D. All right, well, I have x to the fourth plus 8x cubed, plus 7x squared. X to the fourth plus 8x cubed plus 7x squared. Now notice there's a 1 here, really, an 8 and a 7. So there, in terms of GCF, there is no numerical GCF. The GCF here is simply x squared. And in fact, right, when I factor out an x squared, I'm left with x squared plus 8x plus 7. All right, now I want to think about two numbers that have a product of positive 7 and a sum of positive 8. Those are pretty easy. There's only two numbers that really kind of have a product of 7, and that's 1 and 7. And thankfully, 1 plus 7 is in fact 8. So all of this then boils down to x squared times x plus 1 times x plus 7. That's it. All right. Now we've been concentrating on ones where we've got a trinomial that we're trying to factor completely. But there's one other situation we need to take a look at. All right. Complete factoring can also involve the difference of perfect squares, which we saw a few lessons ago with conjugate pairs. Now the key, as before, is to first look to factor a GCF out from the polynomial. That's absolutely critical. All right, you don't want to try to factor until you've done that. So let's take a look at exercise number 4. Write each of the following binomials in completely factored form. Letter A, 2x squared minus 18. Awesome. So 2x squared minus 18, right? When I look at the 2 and the 18, it's pretty obvious that they have a common factor of 2. So I can begin by writing this as 2 times x squared minus 9, right? 2 times x squared minus 9. Now once I do that and I see x squared minus 9, that should automatically make me say, oh, that's the difference of perfect squares, right? X times x minus 3 times 3. And we should now feel comfortable with the fact that we can factor the difference of perfect squares into this product of two conjugates. So that is simply 2 times x plus 3 times x minus 3. And again, the x plus 3 and the x minus 3 could be flip-flopped. That doesn't make any difference. All right, let's do letter B together. Here, we have 5x cubed minus 20x. So I look at the 5 and the 20, right? And the biggest number that goes into both of those is 5. Then I see an x cubed and an x to the first, and I know I can factor an x to the first out of that. So I can begin by pulling out a GCF of 5x. Now when I do that, what times 5x gives me 5x cubed? Well, that's x squared. What times 5x gives me 20x? And that's 4. So now I have 5x times x squared minus 4. X squared minus 4, again, is the difference of perfect squares. X times x minus difference, right? 2 times 2. So I can now factor that as 5x times x plus 2 times x minus 2. Okay. What I'd like you to do now is pause the video and take an attempt at letter C and letter D. All right, let's do it. So first thing I'm going to do is letter C, and I'm looking at that 12x squared minus 3. I look at the 12, I look at the 3. The biggest number that divides into both of them is 3. There is no x that comes along because that 3 doesn't have an x on it. So first things first, right? I'm going to factor a 3 out, and of course 3 times 4x squared will give me 12x squared. And then minus 1. Really, really important that you have that minus 1 there. Now, just like all the problems in this particular exercise, 4x squared is the difference of perfect squares, right? 4 is 2 times 2. X squared is x times x. Here's my difference. And 1 is 1 times 1. So all of this now factors into 3 times 2x plus 1 times 2x minus 1. Almost had 2x plus 1 twice, which would be definitely wrong. All right. Very similar, letter D, 54x squared minus 24, right? I'm looking at 54, I'm looking at 24, and I'm thinking, all right, well, what number goes into both of those, right? And I might have to think about this one a little bit more because I got the 24, the 54, but 6 will go into both of them, right? 6 divides into 54 9 times. 6 divides into 24 4 times. And there is no variable in my GCF, just the number 6. So 6 times 9 is 54, and the x squared just comes along, minus 6 times 4 is 24. Again, I like what I'm seeing inside of that parentheses because 9 is a perfect square, x squared is a perfect square, I have a difference, and 4 is a perfect square. Whew. All right, so these things then factor as 6 times 3x plus 2 times 3x minus 2. And that's it, right? So complete factoring, basically, complete factoring in this course is a combination of GCF factoring first, followed up by either factoring a trinomial or factoring the difference of perfect squares, all right? Or no factoring at all, because once you factored out the GCF, there's nothing else that you can factor. And that definitely comes up a fair amount, don't get me wrong. Today, though, we're concentrating on two-step factoring processes. Okay, let's take a look at one final problem. Exercise number 5. A rectangular prism, i.e. a box, has a volume given by the expression 5x cubed plus 65x squared plus 150x. Its height is given by 5x, and its width is given by x plus 3, where all dimensions are in inches. An expression for its length is not yet known. Find a binomial expression in terms of x for the length of the box. All right, well, I'd like you to think about this a little bit and maybe start by thinking about how is the volume of a box calculated? How is the volume of a box calculated? And see if you can use that somehow to figure out what the length of the box is as an expression in terms of x. Pause the video now and think about this a bit. All right, well, keep in mind, right, that the volume of any box is length times width times height, or I could rearrange this and say it's height times width times length, right? In other words, the volume of a box is the product of this, and whatever that is that's missing. Let me write that volume down, right? My volume is 5x cubed plus 65x plus 150. Now, given that volume is the product of three things, then if I can write the volume as a product, which is what factoring is, then hopefully I'll be able to figure out the missing portion. Well, the first thing I might do, whoops, I'm sorry, that's 150x, and that's x squared. The first thing that I might do is factor a GCF out. Now, clearly, 5, 65, and 150 are all divisible by 5, so that's part of the GCF. And x cubed, x squared, and x, right, also allows me, right, to pull out an x. So I'm going to first factor a GCF of 5x out. Now, when I do that, what do I have left? Well, inside, I'm going to have x squared, all right, plus 65 divided by 5 is 13x, and 150 divided by 5 is 30, right? So far, I know that the volume, 5x cubed plus 65x squared plus 150x, can be rewritten as 5x times x squared plus 13x plus 30. But now I can factor this trinomial, right? I need to just find two numbers whose product is 30 and whose sum is 13. But that's pretty easy, right? That's going to be 3 times 10 and 3 plus 10. So I can now write all of this as 5x times x plus 3 times x plus 10. Okay? Now at the end of the day, how does that help us? Well, keep in mind that the volume is height times width times length. I know the height is 5x. There's my 5x. I know the width is x plus 3. There's my x plus 3. So that has to be my length. So my length must equal x plus 10. All right, it's got to be, right? It's the missing part of the product. All right, let's take a look at letter B. I'm going to actually fill this in right here too. Forget about that anymore. It's x plus 10. Actually, I probably shouldn't cross it out. It makes it look like an x. All right, so I got 5x, x plus 3, and x plus 10. Let's take a look at letter B. How many inches greater is the length of the box than the width of the box? Justify your answer. All right, that seems kind of weird that we can even make this call, but take a look at what we've got sitting here and see if you can answer this question. Well, it's 7 inches larger, right? Or 7 inches longer or whatever, right? Or 7 inches greater, right? Here's the width of the box, x plus 3. Here's the length of the box, x plus 10. So the length with equals x plus 10 is equal to x plus 3 plus 7, which is equal to the width plus 7. So 7 inches longer. 7 inches longer. Doesn't matter what x is, right? If this is x plus 3 and that's x plus 10, then that one is 7 more than this one. Here it is, right? X plus 3 plus 7. All right. And finally, letter C. If the width of the box is 8 inches, then what is the volume of the box? Include proper units. All right. See if you can figure out what the volume of the box is with proper units if the width of the box is 8 inches. Well, the cool thing is, as soon as we know what the width of the box is, we also know what the value of x is, right? So the width of the box is 8 inches, and the width here is x plus 3, right? So x plus 3 is 8, which means x obviously is 5. That's not what they asked me for. They asked me for the volume. The volume, remember, was 5x times x plus 3 times x plus 10. So the volume is going to be 5 times 5 times 5 plus 3 times 5 plus 10. Woo! So the volume is going to be 25 times 8 times 15. Let's see, 25 times 8 is 200 times 15. 200 times 15 is 2 times 15. That's 30, plus another couple zeros. That's going to be 3,000. And since it's inches times inches times inches, that's going to be 3,000 cubic inches. All right. Kind of cool, right? And just one particular, I guess, application of factoring. Maybe a little bit contrived, but whatever. We'll live with it. All right. Let's summarize. Today, we really saw the final piece in our factoring. All right, we're going to do some more challenging factoring here and there, but ultimately, this is kind of the final piece, which is factoring an expression until nothing else can be factored. Now, what does that really boil down to? It boils down to step 1, see if there's any greatest common factor that can be first factored out of the expression. If you can, awesome, do it, right? Whatever thing you have left over is going to be simpler anyway. Once you've factored out a GCF, then look to see if you either have the difference of perfect squares or a trinomial that you can factor. Either way, you then do that factoring and you're done. We're talking a 2-step process at best. All right. In the next lesson, we will get into some slightly more complicated factoring, but at the end of the day, we've basically seen all of our factoring techniques. All right. I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.